Welcome to Rise Learning Machines seminars. We are awaiting the arrival of the speaker, and meanwhile, I'll just tell you a couple of words of welcome. Rise is Sweden's research institute with 3,000 people working on topics spanning from bioeconomy to digital systems. Specifically, the computer science department works on applied AI projects for the benefit of society, and we organize the weekly Learning Machines seminars as part of our Center for Applied AI Research. This meeting will be recorded, and if anyone wants to be removed from this recording, please let us know. Make sure also to check out the collection of great talks on our YouTube channel. I think that...
Hello, can you hear me?
Yes. Hello, Ricardo.
Hello.
Just giving a couple of words of introduction, and then I'll hand over the word to you, if that's okay.
Right. Very good. I'm setting up my camera.
Great. So today I have the pleasure to introduce Ricardo Vinuesa. He's an associate professor at KTH in Stockholm. He's also a researcher at the KTH Climate Action Center and vice director of the KTH Digitalization Platform. He obtained his PhD in mechanical and aerospace engineering from the Illinois Institute of Technology in Chicago. He works on numerical simulations and data-driven methods for complex wall-bounded turbulent flows, such as boundary layers developing around wings in urban environments. In many of his works, he's using technologies such as autoencoders and deep reinforcement learning. He has obtained the ERC Consolidator Grant, the Göran Gustafsson Award for Young Researchers. And today's topics is going to be about modeling and controlling turbulent flows through deep learning. So with that said, please, Ricardo, the floor is yours.
Thank you very much for the kind introduction. Can you see my slides?
Yes, it looks good.
Perfect. And thanks again for inviting me to present in this seminar. I'm going to tell you about my work on modeling and controlling turbulent flows through deep learning. And I am at the Department of Engineering Mechanics at KTH in Stockholm. So I'd like to start. Can you see the next slide now?
Yes.
Yeah, perfect. So I'd like to start with this introductory slide from Airbus, where we can look at a typical airliner and assess the various contributions to the total drag. Around 40% of the drag in an airplane comes from friction, which means that looking at turbulent boundary layers is a good approach to be able to understand the total drag. And around 40% of the total comes from lift-induced drag. So that happens in finite wings, basically because of the pressure difference between the pressure and the section sides. One can actually see these wing tip vortices that are having an important effect on the total drag. So looking at turbulent wings, and in particular I'm going to look at the laser pointer, which you can see now. So in particular, looking at wings that are finite, we can understand around 90% of the total drag in a turbulent wing, essentially. Now, the type of the way in which we use this analysis is to use numerical simulations. We use the spectral element code NAIC 5000 developed by Fisher and others. This code combines the geometrical flexibility of finite elements and the high-order convergence of spectral methods to be able to simulate with very high accuracy geometries of quite some complexity. That's what you can see here at the bottom right, where I'm showing you a simulation that we performed some years ago. This is a turbulent wing at Reynolds number of 400,000 simulated with DNNs, so where all the scales are actually properly simulated. Now, we can generate massive amounts of data, very, very complete databases that will help us to produce better data-driven models using machine learning. So what you see here is a range of simulations in turbulent wings. This is a NACA 4412 wing section, where the first Reynolds number is 100,000, but we go all the way up to 1 million. And this database can be found in this reference, and Vinuesa and others. This is an article in the International Journal of Heat and Fluid Flow, where we can actually show, you can share all the data on these very detailed flow simulations. In this case, the Reynolds number is at 1 million. This is a quite high Reynolds number where the aerodynamic properties of the section, of the wing section, are already relevant to those of the full-scale application. And you can actually say that even if it's a very large simulation, over 2 billion grid points on the computational mesh, we can see that we already have some limitations in terms of the geometry. So these very elongated elements lead to very high aspirations, which in principle preclude us from really computing very, very high Reynolds number configurations. Something that can be done is to go in the direction of adaptive meshing. So being able to have a mesh where automatically we find refinement in the regions where we need more resolution, and due to the non-conformal meshing, we can actually have quite coarse elements close to the far field. And this case that you see here is a finite wing with a rounded wingtip, where we can actually see the wingtip vortex rolling from the pressure to the suction side, and really this vortex is actually being tracked by the resolution that we have in the mesh. And this very complex situation will really help us to obtain very good data and a very good representation towards understanding the contributions of the total drag in a wing. So armed with all this variety of databases, we can actually, I'm going to show you this video, we can actually see how it's possible to, let's make sure that it works, how it's actually possible. Actually, it doesn't seem to play. Otherwise, I will show it outside the, okay, now it should work. So you can actually see the level of detail that we obtain in our simulations. This is a wing that is finite with a rounded wingtip. This is a simulation of 1.5 billion grid points using adaptive meshing, and I'm showing you vortical structures. So these are basically coherent vortices which contain very high vorticity. And these are very characteristic of turbulent flows. Now, what I'm showing you in this visualization is the possibility of actually understanding how the wingtip vortex is rolling up from the pressure to the suction side, and the effect of this vortex on the aerodynamics of the wing. And so what this vortex is doing is that it's basically pushing down the weight because of the rotation, and that action is producing less capacity of the wing to extract lift from the flow, and therefore it has an additional component which is the lift-induced drag. And this is the 40% that I was mentioning at the beginning. So basically, being able to use these very detailed flow simulations, one can actually try to understand a lot about the aerodynamics in these complex flow cases, and hopefully not only improve our understanding, but also improve our aerodynamic design. This now here you can really see in a lot of detail how the wingtip vortex is rolling up from the pressure to the suction side. You can see these vertical structures on both the suction and the pressure side boundary layers, and you can see how there is a partial relaminarization of the flow due to the span-wise pressure gradient of the wingtip vortex induced on these turbulent wings. And here we can see from the other angle how the wake looks like with partial relaminarization, and how the turbulence around the wingtip vortex is actually leaving quite some rotation around there. So in particular, you can see how these very, very detailed flow simulations can be used to produce highly accurate data. And this data, we're going to be able to exploit it to develop machine learning applications. Okay. This is, by the way, work by Siavas Tosi, a senior researcher in my group. He's presenting it in the LES these days. The conference is happening these days. And actually, you can see quite some possibilities of data-driven approaches with these databases. Okay. So if we focus now more on the concrete applications of machine learning, I mean, traditionally, there has been a wide variety of machine learning applications to fluid mechanics. I mean, starting 20 years ago with the work by Petros Komosakos, where he used neural networks to model the near-world region of a channel. More recently, there has been quite some work on subgrid scale modeling, definition of inflow and boundary conditions, flow control, RANS modeling, and even physics-informed neural network spins to try to improve some of the sensing and experimental measurement in a number of configurations. So there's quite some potential with machine learning and fluid mechanics. And in this presentation, I'm going to give you several examples of these possible areas of influence. In fact, earlier this year, together with Steve Branton, we published a review paper in Nature Computational Science. You can see the full reference here at the bottom, where we highlight the potential of machine learning for CFD, for computational fluid dynamics. So we highlight that machine learning can help to accelerate direct numerical simulations. Machine learning can also help with improved modeling of RANs and LES. And also we can use machine learning to improve the development of reduced order models in quite some complex configurations in a very robust way. So in fact, we can really benefit from a wide range of machine learning applications in the context of computational fluid dynamics. Now, the 5 examples that I'm going to give you are listed in this list. The first one is non-intrusive sensing. And in non-intrusive sensing, what we do is that we consider quantities that can be measured at the wall, and we're going to try to predict the flow above the wall with those wall quantities. And the motivation for that comes from basically from the possibility of doing flow control, of being able to sense and control the flow. So in this example, the blue plane that you can see here, that one is the input, and that's the measurements that I'm actually taking as an input. And this yellow plane would be the output. So those are the quantities that I'm actually predicting. Now at the wall, we're going to consider the wall shear stress components and the wall pressure. And I'm going to be using computer vision-based applications like convolutional neural networks to predict the 3 velocity fluctuations above the wall. So using information at the wall and predicting what happens above the wall. And this is work by Luca Guastoni, published in the Journal of Fluid Mechanics. So all the details can actually be found on this article in the reference that you see at the bottom. Here I will highlight some of the most relevant conclusions when it comes to the potential of sensing. So sensing is important because it's much easier to measure at the wall than to put a sensor in the flow and disrupt the flow fluctuations. So what we do is that we produce 2 databases. One, actually both are direct numerical simulations, one at a friction Reynolds number of 180, another one at a friction Reynolds number of 550, which starts to be already turbulent with quite some scale separation. And we're going to train neural networks to connect the wall information with the fluctuations above the wall. Of course, this can be done in different ways. One could use fully connected neural networks. The problem of the fully connected networks is that they're not allowing us to exploit the spatial information in the data. That's why convolutional neural networks, which you can see at the bottom, are much more convenient because, of course, turbulent flows have a quite pronounced spatial behavior. So we can try to exploit the coherent structures in the flow through convolutional neural networks. And in a convolutional neural network, I have this input map. Basically, that's my image. This little window, this is a kernel, which allows me to swipe through the input, and applying convolution operations, I can try to really see how the data in the input is distributed in space to be able to exploit those spatial correlations in the data. So CNNs, convolutional neural networks, are very widely used in computer vision for this reason. Now, the idea is that, so here you can see one of our architectures. This is a CNN with 6 hidden layers, and you can see the number of filters that we have per layer. We have 3 inputs, which are the 2 wall shear stresses and the wall pressure. We have 3 outputs, which are the 3 velocity fluctuations. And as you can see, a CNN is basically going to, in the first layers, identify more abstract and smaller features in the data, like edges or regions of recirculation. And through the concatenated application of convolutions, I am progressively building towards elements which are less abstract, so more concrete, and they're larger. So I can hierarchically build the coherent structures in turbulence that you saw at the beginning in the video through simpler elements that are identified in the first layers. Okay. So now what we have is on the left, the inputs, the wall shear stress components and the wall pressure. On the right, the outputs, which are the string-wise, wall normal, and span-wise fluctuations at a particular wall normal location. The results are at Aritau 550. And again, all the summary of all this data can be found in JFM, in this reference that you can see here at the bottom. Now, what I showed you so far were predictions based on the full plane as an input and then the full plane as an output. So this is what we call the FCM, the fully convolutional network. But there's another method which we call FCM POD, which combines the fully convolutional network with POD, that's proper orthogonal decomposition. This method is also known as PCA, principal component analysis, in many other areas. Essentially, this method allows us to decompose the spatio-temporal problem into spatial modes and temporal coefficients in such a way that the neural network only needs to predict the temporal coefficients. So that, in some cases, can actually be beneficial. If we look at the instantaneous stringwise velocity fluctuations, the first column is at y plus 15, which is quite close to the wall. The second column is at y plus 100, so that's farther away from the wall. What you can see is that the reference is the third row. So this is the flow that we're trying to predict. This is my reference. And the first row is the extended POD predictions. So in the extended POD, which is formally equivalent to linear stochastic estimation, I have a linear relationship between the input at the wall and the output above the wall. And of course, turbulence is inherently nonlinear. So the extended POD will be able to reproduce the linear superposition, so some of the linear mechanisms, but not the nonlinear ones. And you can see by comparing the third and the third rows, so the first and the third rows, that the linear method is leading to attenuated fluctuations. And also we are missing a lot of the details of the nonlinearity of the spanwise movement of the streaks as a consequence of the linearity of the model. If we go and compare the third and the fourth rows, what we see is that near the wall, the FCN method is in excellent agreement. So I can actually predict very, very well the flow close to the wall. And farther away from the wall, the FCM POD method is better. So it's not perfect, the prediction, but it's actually better because I'm able to identify where the streaks are. So close to the wall, the highly disorganized flow with a wide range of scales is better predicted with the FCN. Farther away from the wall, what I want to use is the FCM POD, where the fluctuations of the large scales are effectively encapsulated into few POD modes over which I can just calculate my coefficients and quite effectively get some of the behavior that I want to have. So that's essentially the comparison for the instantaneous flow fields. What I'm showing you now are the turbulence statistics. So these are the stringwise, wall normal, and spanwise Rho mean squared fluctuation profiles. The black line is the DNS, so that's the reference. The triangle is the FCN, so that's the fully convolutional network. The dot is the FCN with POD, and the square is the linear method, that's the extended POD. And you can see that near the wall, the near wall peak of U prime is predicted with less than 1% error, which is excellent with the FCN method. As I move farther away, the FCN POD gets better, and we get around 26% error for that prediction. The linear method is worse than the nonlinear ones, as we indicated, because turbulence is nonlinear and is, by construction of the model, unable to reproduce all the complexity of the interactions that happens in turbulent flows. One tool that is quite helpful is what we call transfer learning. So in transfer learning, we can transfer what we learn in one task to another task that is not too different, but not too similar to the original one. In this case, we want to use a network trained to predict at y plus 15, so close to the wall, and see how we can transfer what we learn for another network predicting farther away from the wall at y plus 15. So in that case, what we do is that we freeze the three first layers, because the three first layers are targeting features that are more similar and smaller, close and far away from the wall. But the three last layers, which are going to be focusing on larger features, those ones are retrained. Okay, so I only retrain the three first ones. I transfer so the three last ones are retrained. The three first ones are transferred. And what we get is the same level of accuracy, but we reduce the training time to 23% of the original. So we reduce the training time to a factor of more than 4. So transfer learning is actually quite effective in the context of turbulent flows. This also happens when I take a network to predict at Reynolds number 180, and I take those weights to start the training at Reynolds number 550. So in the high Reynolds number case, I compare the case when I transfer the weights, And when I start from random initialization of those weights of the network, what I find once again is that I can reduce the amount of training data by a factor of 4. And that's interesting because, of course, the higher Reynolds number data is much more expensive computationally. So being able to focus on most of the training on the low Reynolds number one and reducing the use of expensive data by a factor of 4, that's extremely, extremely valuable. So that's basically a quite helpful technique with transfer learning that can really have many applications in the context of turbulent flow, but also other engineering applications.
Ricardo?
Yeah.
Could you please repeat the transfer? Where is it transferred from and to?
Yeah, this example or the previous one?
This example.
In this example, we have one network to predict that friction Reynolds number 180. So that's the low Reynolds number with all the weights. And then we take another network to predict at a higher Reynolds number. And we transfer the weights.
I see.
So in the high Reynolds number case, I start the training from the weights that were transferred from the low Reynolds number case.
And this number, it has to do with the friction in the material.
Yeah, that's the Reynolds number. So the Reynolds number measures basically the ratio of the inertia to the viscous forces in the flow. So a higher Reynolds number will give me a more turbulent flow in a way, a much more turbulent condition, much more chaotic in the flow behavior.
Okay.
So the more chaotic case, the high Reynolds number case, is much more expensive to simulate, but I can reduce by a factor of 4 the need of data at the high Reynolds number case because I can exploit what I had from the low Reynolds number one.
Interesting.
Okay, thank you. With the same accuracy, basically. So I can reduce by a factor of 4 that requirement of training data. So that's one example where I'm doing sensing from the wall to above the wall. So far, I have assumed that the data that I have at the wall has full resolution, and that is very, very detailed. But in reality, if I do an experiment, I will only have a few measurements at the wall. So to be able to represent that, we're going to use downsampling. So we're going to take the information at the wall, and I'm going to skip points to reduce the resolution. And to be able to do prediction tasks in this configuration, we will use an architecture called GANs, so generative adversarial network. This is this architecture that we see over here, in which we have two parts. We have a generator that has the task of producing high resolution images from low resolution ones, and a discriminator which has the task of differentiating whether a high resolution image is true or it was produced by the generator. So these two networks have antagonic roles, and they're trained together using game theory in such a way that they both get better and better at their own jobs. So in the end, I have a generator which is really good at producing quite realistic images in high resolution. And I'm using this architecture as follows. So we are having, so I have a question in the chat. I don't know if I should take it at the end or should I take it now? What do you think, Olof?
I think it's mostly up to you. If you think it's time to take a question, then do so. Perhaps this is more of a comment. Based on Reynolds numbers, we classify the flow into laminar and turbulent flow.
Yeah, that is correct. Although in this case, all the flows are turbulent. So we always have turbulent flows. And then the higher Reynolds numbers are more chaotic, let's say. I mean, at very, very low Reynolds numbers, then you will have laminar flows. That's correct. So the point is that we use very coarse inputs. We have here, we reduce the resolution of the inputs. We apply GANs to have super resolution. So we have inputs at the wall with high resolution. And using those inputs at the wall, I predict the flow above the wall with high resolution. So in a first step, I increase the resolution of the input. In a second step, I make the predictions above the wall. What I'm showing you at the bottom is the instantaneous streamwash wall shear stress. This is the DNS, so this is the reference. On the top row, I'm reducing the resolution of the input, so I'm downsampling by a factor of 4, 8, and 16 squared. And in this case, you can see that the input is actually very coarse. So this is basically what I will have in an experiment. And in the second row, I'm showing you the predictions. Now, the second row is to be compared with this panel, with the DNS. You see that the predictions are in good agreement. The more downsampling, the worse the agreement, but I'm always finding streaks in very good agreement with the reference. So I'm having the right size of the streaks, the right spacing, the right locations. So basically, I can get very physically realistic images, even if I have very, very coarse images. By the way, this work is by Güemes and others, is in physics of fluids, and this is the reference. So you can find all the details of this GANs architecture in this reference over here. Now I'm showing you my predictions above the wall. So the columns show Y plus 15, 30, 50, and 100. So I'm going farther away from the wall. The first row is the DNS, so that's the reference. And the subsequent columns are showing me the results with more and more downsampling. And here I'm always showing the stringwise velocity fluctuations. So of course, the easiest prediction is this one over here, where I'm predicting very close to the wall with very little downsampling, and the agreement is excellent. And the most challenging prediction is this one. So this panel over here with the highest downsampling and the highest distance to the wall, which I should compare with the panel over here. Now, what you can see is that, of course, there is a difference between the prediction and the reference flow, but the streaks are still very well represented. So if I want to do large-scale control, if I want to tackle those large-scale streaks, I can still do that based on the information that I have from these GANs. Okay, I'm going to read the chat. There's a couple more comments. Could you please explain your experimental results? How many experiments did you have? What was the variation in your data? Did you consider time dimension in your calculation? So, I mean, this is all based on numerical simulations. There is no experimental data. But in this downsampling, in this example that I'm showing you with the GANs, I am trying to mimic the resolution that you will have in the experiment. But this is all based on numerical data. There is numerical simulation data. How many experiments? I mean, I guess you mean how many snapshots. So this requires on the order of 10,000 snapshots for this training, this supervised training. Of course, when I am doing transfer learning, I significantly reduce the need for snapshots, for label snapshots. And then the time dimension, basically, so the variation in the data were the subsequent instantaneous time steps. So obviously the instantaneous flow field is changing all the time. And the variation, which you can assess it based on the stringwise velocity fluctuation profiles that I showed before. The time dimension is a good point. These results are based on having for one instant the information at the wall and predicting at the same instant above the wall. If you consider the time sequence, you can gather information from various inputs and exploit the temporal information in those predictions. That doesn't improve the results significantly. There is a mild improvement, but the most dramatic aspect of these predictions comes from the spatial information. And that's the important thing. Okay. I hope that answers the question. Now, if we go to the next example, so I showed you predictions from the wall to above the wall, but there is another possibility of predicting from far away from the wall to predict closer to the wall. And that has the motivation of developing wall models. So basically the idea of trying to replace a big part of the expensive simulation by just having a boundary condition over there. And this is work published in Archive. So you can see the details over here. What we're going to do is use a convolutional neural network to predict the flow close to the wall based on flow far away from the wall. That's basically the approach that we're going to take. So what I'm showing you is basically the instantaneous U, V, and W fields. So the stringwise, wall normal, and spanwise fluctuations. The input is at Y plus 100. That's the first row. The second row is the predicted target. That's at Y plus 50. So the first plane is here. My target plane is here. And on the third row, I'm comparing my predictions with the second row. So I want to make sure that the second and third rows are in good agreement. And what we can see is that the U prime is in quite good agreement. The V and W exhibits a bit more deviation, although still is quite okay. Turns out that to predict from far away to closer to the wall is much harder than the previous prediction, because the wall contains all the information of the small scales. But when you try to use the information far away from the wall to predict closer to the wall, you're missing the information about the small scales, and you're also having, well, you need to reorganize the way that you use your receptive field in order to exploit the information more effectively. This is manifested in the power spectral density. So what I'm showing you here are the stringwise wall normal and span-wise pre-multiplied power spectral densities. The gray contours are basically the reference, and the orange lines the prediction. So you can see that I'm effectively missing part of the small scales. The larger scales are reasonably okay predicted. I have overall 19% error in this prediction, which is a reasonable prediction, actually. It's a reasonable level of error. But if I want to use this for a wall model, I need to do something else. So a purely supervised approach is maybe not the most adequate method. Maybe we need to do something else. And to that end, one can actually use GANs, to be able to reconstruct some of the missing scales, and also to play with the receptive field with max pooling and things like that. Reinforcement learning is an approach to avoid the supervised learning and trying to come up with something more nuanced when it comes to the possibilities for wall model development. Okay. In my fourth example, I'm going to talk about reduced order models. And of course, some classical reduced order models approaches can be POD or PCA. So this is a linear method in which I obtain a linear superposition of modes, which by construction are orthogonal and are ranked in terms of their contribution to the reconstruction of the signal. Now, the orthogonality is good because orthogonality allows me to obtain modes that are more interpretable physically. But using nonlinear methods such as autoencoders does not ensure the production of orthogonal modes. Now, in this study, we're going to try to use autoencoders to obtain modes that are nonlinear, but also orthogonal, and that are also ranked in terms of energy contribution. Now, this is work by Hamid Reza Ibasi, and is published in X Persistence with Applications. And so this is the reference, so feel free to also check the details there. And this is the database that we will consider. So this is a high-fidelity simulation of the turbulent flow in a simplified urban environment. You can see the level of detail that we can obtain in this simulation, and we're going to predict the horizontal plane at the mid-height between the two obstacles. We have a total of 1,200 images to perform these predictions. Okay. So the first method is basically a convolutional neural network autoencoder. Now, convolutional neural networks are good for turbulent flows because I can exploit the spatial information in the data. And the autoencoder, what it does is that it starts with the original data. It progressively downsizes and reduces its dimension until we shrink it in this latent space, in this bottleneck. And later on in the decoder, I upsample in order to obtain the original data again. So the goal is to obtain in this bottleneck, in this latent space, a quite effective latent representation of the original data. So a quite effective compressed representation of the original data. Now, this convolutional autoencoder will not give me modes that are orthogonal, neither ranked in terms of their energy reconstruction contribution. The framework of hierarchical autoencoders developed by Fukami and others that allows to obtain modes that are hierarchical. So they are sorted in terms of their contribution to the energy reconstruction. Now, in the hierarchical autoencoder framework, I start with an autoencoder in which the size of the latent space is 1. That gives me a first latent vector R1. Then I have another latent autoencoder with a latent space of size 2. That gives me, and I fix the first latent vector that I obtained before, which means that I will only obtain one more latent vector R2. And if I do this sequentially, then I get a number of latent vectors which has less and less contribution to the reconstruction of the original signal. So these modes are hierarchical, but they're still not orthogonal. Okay. If I want to have orthogonality, then I can use the framework of beta variational autoencoders, which allows me to introduce a stochasticity in my latent space. So P of X will be the distribution of the original data. P of R would be the distribution of the data in the latent space. What I want to do is maximize this function, which is the marginal likelihood. This is the approximation of P of X given the parameters theta. And I have two conditional probabilities. In this one, I have a decoder, which will take me from the latent to the original space. And in this one, I have an encoder, which takes me from the original to the latent space. Now, I have that the encoder is a Gaussian distribution with a mean and a standard deviation. I can sample with auxiliary noise, which is also Gaussian. And the loss function in this case looks like this. So I have the reconstruction term plus an additional term with a hyperparameter, which allows me to promote learning variables that are statistically independent in the latent space. Okay. Now, what am I doing here? Well, I want to have variables in the latent space which are statistically independent, and also I want to promote learning a parsimonious model. So I want to end up having a latent space that is disentangled and also parsimonious. Okay, so many of them are actually zero. And this is what the setup looks like. So of course, my latent space, I will decode it with the decoder, and I can encode from the original to the latent space using the encoder. And in the latent space, I have my mean, my standard deviation, and the noise that I use for the sampling. This is what the flow looks like. These are the instantaneous stringwise velocity fluctuations. This is my reference. If I take POD, the proper orthogonal decomposition or principal component analysis, with 5 modes, I only reconstruct 30% of the energy. And all the autoencoder-based approaches give me around 90% of the energy. If I focus on the flow between the two obstacles, I can see all the details here. And I can see that the POD is not able to identify any of these particular concentrated regions of high or low speed. All the autoencoder-based approaches are able to really identify and properly reconstruct all these regions of high and low speed and low fluctuations in the region between the two obstacles, which is actually quite interesting. This means that autoencoders allow me to have a much better way to compress data. If I want to build a reduced order model, the autoencoders are going to be a much better approach than the POD. However, are these modes orthogonal? Well, the POD, which is based on linear algebra, is naturally orthogonal, but the beta variation autoencoder gives me over 99% orthogonality, which is fantastic because that really allows me to have very good orthogonality in my modes. The two other approaches are not really orthogonal, as we can see from the determinant of the cross-correlation matrix, which means that that will have problems when it comes to interpreting the meaning of these modes. Now, if I go into the effect of the penalization factor beta, what I know is that a larger value of beta will reduce the quality of the reconstruction, because of course my loss function has one term which is the reconstruction, and another one which is the orthogonality. But larger values of beta will give me much more orthogonality, going over 99% orthogonality for the largest values of this hyperparameter. So we want to find a good balance in this beta variation autoencoder where I can have orthogonal modes and still a good reconstruction of my signal. Now, why do I want the orthogonality? That's what I can see here. These are the first 5 POD modes. And of course, my case has a pronounced large-scale shedding, which the POD is able to effectively reconstruct. Both the convolutional autoencoder and the hierarchical autoencoder are able to give me modes that are basically noise, high and low frequency noise. But the beta variation autoencoder, which is the first column, gives me modes that have a physical interpretation. So in fact, I can obtain modes that are quite similar to the POD modes with some turbulent fluctuations superimposed on top of them. And that's actually very cool because this means that with the variational autoencoders, with the orthogonal autoencoder modes, I can obtain a quite effective representation of the original system. I can have a very good reduced order model where I can, with very few modes, reconstruct large fractions of the energy. And that's the idea, that I can have a very compact representation of the original data I don't need 800 modes to reconstruct 90% of the energy. I only need 5. And those modes are actually interpretable. So I'm actually able to gain some physical insight from those modes that I can actually obtain. Okay? And by the way, the beta variational autoencoder modes are not only orthogonal, but we can also sort them in terms of their contribution to the reconstruction. So these modes are also, well, ranked in terms of the reconstruction contribution. So again, the reference is here in expert systems with applications. I believe this is a very promising approach for reduced order models, not only in fluid mechanics, but in a number of complex physical systems, basically. Okay. And now my last example is to use deep reinforcement learning for flow control. So in deep reinforcement learning, this is basically what I'm having. I have an agent, which is the neural network. This agent interacts with the environment, which is the flow simulator. That's where the environment where I'm simulating my flow. And that interaction is done through actions. So these actions change the state of the environment. And that means that informs the agent on the new state of the environment, but also those actions will give me a certain reward. And the reward is a measure of the quality of those actions under a certain norm. So my goal with deep reinforcement learning is to find a policy pi, which given the state of the system can provide the optimal actions to optimize the expectation of the maximization of the reward. And that's what I want to have. The advantage of reinforcement learning is that learning is not supervised. So I don't tell the model what it needs to learn. I just give it a reward, and the model learns by itself what it should be doing to maximize that reward. We start with a simple example, which is a 2D bubble, a 2D separation bubble. And what I do is that I actuate upstream of this bubble to be able to reduce this separation length. This is a quite classical problem, which can be performed with periodic forcing. So I find a frequency and I force the flow. But in this case, we're going to try to do something a bit more nuanced with the reinforcement learning. So this is what the flow looks like. The color region is the negative velocity. So basically the bubble, the recirculation bubble. These dots are the probes where I'm measuring my flow. The square is the region where I'm actuating, and I'm using a volume force to set up the actuation, mimicking blowing and suction. And this arrow over here, that's the reward. I want to minimize the arrow, which means that I want to minimize the separation length. Now, the key is periodic forcing means to take one frequency and start to force up and down over here. The reinforcement learning will hopefully learn something more nuanced and more sophisticated. And that's something that we can understand by looking at the video on the left. So looking at this video, we can see that the control has at least 2 frequencies. I have a frequency associated with these wave packets that I'm sending, but I'm also having another frequency associated with the length of the separation bubble. So in fact, with periodic forcing, I obtain 20% reduction in the bubble length, but with DRL, with reinforcement learning, I can obtain 30%. So the reinforcement learning is able to find a more effective strategy than the classical one in order to be able to reduce the separation length. So that's actually quite interesting. But even more importantly, if we apply this for opposition control in turbulent channels, so basically I allow the reinforcement learning to devise a control strategy to minimize the friction in a turbulent flow, what I obtain is that the reinforcement learning gives me 40% drag reduction. And the classical method is called opposition control. And you can see an image of the opposition control here. This method is basically aimed at opposing the fluctuations in the near wall region when I'm applying blowing and suction at the wall. That only gives me 30% drag reduction. These results are in a minimal channel, but they're robust when applied to a full channel. And I have to say, this is a very, very promising research direction because if I can control the flow in turbulent configurations, well, I can have more efficient airplane, more efficient piping through oil pipes. So I can actually have very novel strategies to control the flow, reduce energy losses, and reduce environmental footprint of all these applications. So reinforcement learning, I believe, is really going to help us significantly to obtain novel approaches to flow control. Okay. And this is a summary of my presentation. I talked to you about sensing and the possibilities for sensing, also using GANs for super resolution, using autoencoders for model decomposition, and also using deep reinforcement learning for flow control in a number of flow configurations. So you can find my contact information here. This is my email, the web of my lab, also my social media information. So if you're interested in discussing more, feel free to reach out, contact me, and I'm happy to talk more. And for this moment, I'm very happy to take your questions, and I thank you very much for your attention.
Thank you, Ricardo. We have a question in the chat.
Yes. So I saw the question. Thank you, Riaz. So the Navier-Stokes equations govern the flow, and we do what is called direct numerical simulations. So in direct numerical simulations, we discretize the domain with very high resolution, and then we integrate in time those equations to produce the data. And so we obtain very high fidelity representations of the flow based on numerically solving the Navier-Stokes equations. The non-dimensionalization is based on the channel height and the bulk velocity, basically. So I can obtain non-dimensional parameters. So all my data is non-dimensional. And the non-linearity is, of course, introduced. Well, the Navier-Stokes equations are nonlinear. We have the convective term that introduces the nonlinearity. And in the neural networks, we have the nonlinearity through the activation functions, right? So obviously, there we can then introduce the nonlinear aspect of the prediction. Was that clear, Riaz, or you have any more questions? Okay.
Next, we have a question from Stepide.
So,
hello. Thank you for the talk, for your presentation. I have a question. Maybe it's a stupid one. I don't know. You show that you are use transfer learning for using basically fewer samples to model different turbulence level.
yes.
So there are two questions comes to my mind. One is you didn't explain how do you evaluate. There is some randomness in turbulence modeling, and also some randomness comes from the modeling that the result that you get from the machine learning. So how do you measure really that if what you have produced is good enough, or like what if you would have you needed to, or how much this depend on which kind of transfer you are doing, or how much turbulence you are extending to. So I think there are many things missing at least.
So turbulence, of course, you have fluctuations, turbulence fluctuations, because the flow is not steady. What we do, I can go back to the slide and hopefully illustrate it a bit better. I mean, what we do is that we compare with respect to the reference. So we have the DNS. The DNS is the truth. We want to make sure that our predictions are accurate based on that truth. No? So basically, what I'm showing you here are the average fluctuations in the stringwise, wall normal, and spanwise fluctuations. And what I do is that I compare the predictions from my machine learning models with the reference. Okay, so basically, this gives me the deviation in a statistical sense, which is connected with the deviation in an instantaneous sense. This would be the instantaneous comparison. Now, that's your part about the randomness in the turbulence, which is not exactly randomness, it's more chaotic behavior. So of course, one takes that into account by averaging over many snapshots to obtain these profiles over here. Now, the different neural networks that we're training, of course, you start with an initialization of the weights, and then you might end up with different models, slightly different models. That's where there is some randomness, let's say, in the training. What we did is that we trained several neural networks on the order of 5 to 10. And then here on this table, you can see the relative errors that we obtain. So for example, at y plus 15, we get less than 1% error. And this is the uncertainty quantification, basically. So the range of performance of those models that we obtain. So this would be the mean performance. This would be basically the uncertainty of that performance. Now, for the transfer learning, so this is about the predictions, taking into account the chaotic behavior of the flow and the variation of the various models that are being trained. About the transfer learning, in this example, for instance, what we do is that we just take all the weights of the model for the 180, we transfer them to the 550, and then we keep training starting from the weights that were transferred. And I compare the results from that model with results obtained where all the weights are initialized randomly, basically. So I compare those two cases. And of course, when I'm transferring the weights and continuing the learning from there, the accuracy is better because I have already taken into account quite some of the physics behavior from the previous low Reynolds number case. I don't know if there was anything else that, keep in mind that the same network can be applied for both Reynolds numbers because the size of the kernel is the same. The images are bigger at high Reynolds numbers, but the size of the kernel is the same in both cases.
Thank you.
Yeah, thank you. So I think in the chat there were some questions also.
Yes, we have a question from it. How would FCM POD compare to DMD?
Yeah, so DMD is also based on a linear assumption. It's also based on linear algebra. So of course, in terms of being able to, so you're thinking if I combine FCN with DMD, that's what you're proposing, or what is what do you mean exactly with your question?
Yes, can you hear me? Yes,
I can hear you.
Yeah, precisely. So did you actually compare? This is my question. So I assume you compared it to POD. Did you perform DMD? And just for comparison, how would it perform?
Here, the POD, the only reason to do POD is to be able to truncate the system effectively, to be able to do model reduction and truncate the system. POD is going to be the optimal linear reduced order representation of the system. It's going to be more optimal than DMD. So by definition of the optimality of the POD, the FCM POD at this particular task of truncating and predicting is going to be better than DMD. So we didn't do that comparison because that was not necessary. Of course, what could be different is if one thinks of the interpretation of those modes. Then with DMD, one can get maybe interpretations that don't come with POD, but purely for the truncation, POD is going to be better. Now, of course, what will be even better would be to use the autoencoders. So have an FCN autoencoder approach that we haven't done yet, but that will work even better. Yeah.
Thank you.
Yeah. You had two questions. What is your second question?
Well, yeah, it's actually with regards to the future of physics-informed neural networks or physics-informed general AI. Where do you think it's going? Well, some are proposing completely omitting our finite differences or finite element, or just using directly neural networks for solving the PDs.
Yeah.
What do you think about that?
I actually have some work on physics-informed neural networks for PDs. I can show some slides quickly. I think that neural networks, physics-informed neural networks will never replace CFD. Never. I mean, that's my personal opinion. You know, these numerical methods are designed to effectively solve the PDs. Neural networks cannot compete with numerical methods in this sense. I mean, they can't. So to think that PINs or other neural network approach is going to replace CFD is quite naive. I don't think it will happen. However, in some applications, PINs can be better than CFD in some concrete applications. So I have this paper also by Hamid Reza Ibasi, the references in physics of fluids. So you can see it here. And what we do is that we take the 2D Rans equations and we don't assume any model for the Reynolds stresses. We just solve the 2D Rans equations with PINs. And what happens with PINs is that because of the automatic differentiation, we have exact derivatives, which means that I don't need to solve all the gradients with very high accuracy. And this leads to a cost, because I can get away with a mesh that is coarser than an industrial simulation. So I get a cost that is similar to that of an industrial simulation, but I get much better accuracy because I don't need to come up with a model for the Reynolds stresses. The Reynolds stresses are solved within the PINs approach as part of the same PDs. So in this particular example of solving the Rans equations, PINs can outperform traditional CFD solvers, but in general, I don't think that there is any chance that that will happen. I can show you, I get actually very good results. Even in the periodic Hill example, pins is able to get less than 3% error in the mean, very good representations of Reynolds stresses, but again, for very niche applications.
Thank you.
Okay.
Yeah.
2 last questions, one from Hamid Reza.
Yes, do you hear me?
I hear you.
Yeah, thank you very much for the presentation. You showed the prediction when you have some type of sampling from close to the wall in the viscous region, and then you predict the logarithmic region in the upper part of the channel flow.
Yeah.
So do you assume that the wall is smooth, or you can have some type of assumption that the wall is not smooth, and then it includes some roughness?
So this method, this model that I showed is for a smooth wall, but this could be easily extended to rough walls as well. In fact, we're having some work on rough walls and predictions as well. But this is not what I showed today. It can be easily extended, but everything that I showed was for smooth walls.
Thank you.
Perhaps the final question in the chat. If we would like to do research or know more about AI applied to turbulence modeling, where do you think we should start with, especially if we have a background with turbulence?
Yes. Are you asking in terms of references? What are good references to start with?
Yes.
Yes. So, I mean, I would suggest the review paper that I have in Nature Computational Science can be a good place, because I try to provide a good overview of the existing methods and the possible future directions. So it's this one over here. So this is the references here, Nature Computational Science, published this year. So here I really highlight where machine learning can help for modeling, both RANS and LES modeling, reduced order modeling, and acceleration of DNNs. This can be a good starting point. And I see opportunities in all these areas. So machine learning can really help flow simulations in all these areas. Yeah, I mean, the answer, in some cases, you can find better closures. In some cases, you can get a reinforcement learning algorithm to devise new ways of closures, find coefficients. There are many, many different alternatives, but I suggest that you have a look at this paper. And of course, I'm happy to talk to you, have a call, discuss in more detail possible ideas for collaboration. Thank you.
So if you want to quickly...
Yeah, I can quickly address. I mean, I think there is some interest, so I'm happy to answer the. So the term share your data or code. So all the papers that I have shown, the data is available. I mean, the data is available and the codes are available. And if you cannot find it, please contact me, and I will be very happy to provide you the papers, the codes, and the data. So I really have everything open access. Everything is reproducible. So I mean, all of our studies, we have several groups that were able to reproduce exactly the same results. So in principle, I'm happy to share everything and happy to also interact and discuss more. Experience regarding how magnetic and electric field influence turbulence flow. Yeah, that's a whole research area called magnetohydrodynamics. I don't work on that, so I don't have so much experience. The only thing that I have done, I mean, I do some flow control with plasma actuators. So then the plasma ionizes the air and is able to introduce some currents. So in that direction, I have a bit of experience, but magnetohydrodynamics is not my area. There is an extensive literature there that is relevant. Instead of DNS, can we use multiple run simulations to predict the effects of geometrical changes? There is a framework of multi-fidelity. So one can use DNS data of higher fidelity and then more simulations of runs of lower fidelity to try to combine both and get meaningful results. So that's generally a good basically approach, the multi-fidelity approach. Of course, with the runs, you get less accuracy, and that's expected, but multi-fidelity can help to get the best from the high and the lower fidelity ends of the spectrum.
All right. So thank you very much for this talk, Ricardo.
Thank you for the invitation. It was very nice.
Yeah. So next week we actually have no seminar because we're loosely following the schedule of Swedish education system, and there's an autumn holiday next week. The week after that, November 10th, we will have Fredrik Krattet from Google visiting us. He works on rainfall runoff modeling. So welcome back in 2 weeks, and thank you for today.
Thank you very much. Bye-bye.
Bye-bye.